All right, in this video what we're going to do is talk just a little bit about magnetic forces and just do a little bit of a reminder about forces in general. So here I have a charge that's moving with a velocity v to the right, and at some location I'm interested in what's going on with the magnetic field. We developed a model for that told us that if we take the cross product of v and r for a positive charge, we would generate a magnetic field that points out of the board like that. Now that magnetic field can actually interact with other moving charges and apply a force on those charges. In a couple of videos in the future, what we're going to do is talk a little bit about how that force is modeled. But for the moment, the idea is that this interaction that is between the magnetic field that a charge produces and another moving charge results in a push or pull. And so that push or pull we've talked about in terms of a force. And that force we often represent with an F with an arrow on top of it. And that means that it has both a magnitude and a direction. So it has a size and it has a direction. And we'll talk a little bit about how that magnetic field produced by other charges exerts forces on other moving charges. Now the units of the force are newtons. So we've talked a little bit about that in mechanics. But the key thing here is that these forces can act to change the momentum of particles that are moving around. So that is done through the momentum principle, which is namely that the change in the momentum of some particle is related to the net force that's exerted on it over some period of time. Now, in a situation where you actually have a step in time that you can really measure, right, so like a second or a couple seconds or even a microsecond, this force is an average force over that time interval. We can take a very short time step by sort of relating the ratio of the change in momentum to the change in time and find that that's actually the description of this average force, this average net force. If we take the time to be very, very short, it turns out that the exact description of the net force that acts on a particle is the time derivative of the momentum. That is, how quickly it's changing sort of in an instantaneous way. We'll be able to use this form of the momentum principle to describe the motion of charged particles in magnetic fields by using the update form of it, which is that the final version of the momentum is equal to its initial version, or initial value, plus whatever the net force is times delta t. We've referred to this as the update form of the momentum principle. What it tells us is that if we know how fast something is moving and in what direction and how much mass it has, then through the interactions that it has, we can determine what's its momentum in the very next time step. So this was just a sort of reminder of this idea of force and the idea of the momentum principle, which relates the force to the motion of the particles that interact. In the next video, what we're going to do is talk a little bit about what that force actually is when you have a magnetic situation.